All right, better. Okay. This is the one we're looking at, right?
Yep.
Okay, so this one is going to be a little bit of a pain because when we do the limit definition of this, we're going to have to do simplifying of fractions within fractions.
Yeah.
Um, uh, which limit definition did you choose? Did you do the x plus h one? Did you do the b goes to a?
I actually went with the G T hold on. I went to this one. Let's see, can I point to it right there? This one.
Okay, yeah, yeah. Okay, so the time one time goes to another time. Okay, so we could do limit as I'm going to write it just with less subscripts. We'll do b to a of g of b minus g of a all over b minus a. I find this to be the more intuitive formula, but for some reason, when I learned it, the x plus h version is what I was told to memorize, so I default to that quite often. We can try both. Both of them are going to be a little bit of a pain, but they'll work out just fine.
I actually kind of found
Okay,
this one
so
to
let's
be
go
less
ahead
of a
and
pain, to be honest.
this one, you said?
Yeah, when I went through with the other one, I just couldn't finish it.
It's just rough, yeah. Okay, cool. So
Yeah.
that's fine. That's why that's most of the time when I was trying this, when I was rewriting the course, I found this to be the much more intuitive. So that's why it's the one that I promote for you all. So let's begin. We're going to plug in b. So it's going to be b over x minus 2. Nope, yeah, b minus 2. See, I always stall out and I go back to the x's. Okay, b minus 2 minus a over a minus 2 all over b minus a.
Yep.
Now, this needs a limit, so we're going to do the limit as b approaches a. And what am I trying to approach here?
Hmm.
What's the point that we're considering?
Hold on, I'm gonna have to up the volume a bit. It's kind of hard to hear you.
No problem. So in other words, what is the time, like what's the specific x value or the specific time that we're trying to consider?
We're trying to consider okay, so it's just one of those things where I know what it is, but I just can't figure out a way to say it in words.
That's okay. So one way to kind of help to adjust that is let's draw a picture. I like getting our eyes involved whenever I find that words are difficult. So we've got some curve. I don't know what this curve is. Let's just draw some squiggle on the paper. Make sure that it passes the vertical line test so that it's still a function, but that's g. Now I'm looking for g with like some kind of slope, some kind of tangent line. So like I can draw a little tangent line here, maybe make it a different color. So this is a picture of a derivative. We'll use this picture all the time when we're talking about derivatives. The question I have is when? When is this when that we want in the picture?
Oh, okay.
So what is that x value? What is the when
The x
that we're
value that
considering?
we're looking for is 1.
1, very nice. So that means that 1 is what I'm going to try to get close to. I'm going to try to get close to that by moving in towards it. So if I want, I can go back to this structure, and without doing any of the algebra yet, I can say B is trying to get close to what again?
1.
1. So I'm replacing A with 1, and then I can even go through this entire structure,
And
and I
replace
can
A with 1.
replace A with 1. Exactly right. So that's going to make this much more friendly. Now I've got a whole
I
lot
hadn't
less
considered that
variables running
actually.
around.
That's good, yeah.
So now if I want to go through, like we don't have to do a whole bunch of simplifying yet. We'll do what looks nice and friendly, like this fraction up here looks great. So let's just do whatever we see as a good option at the time. And then we have b over b minus 2. This is going to be 1 divided by negative 1. So that's going to be positive 1. So I have a plus 1 here. And then over b minus 1. So this is the exact same story. It's just me giving it details, right? We started with a structure. I should say we started with a structure. We filled in details about the problem. We filled in more details about the problem, and we've got equal signs all the way between. So it's the same thing. We're just making it look friendlier and friendlier. All right. Now, however, if I actually plug in 1 for B as well, I'm comparing something against itself, and that's not a good way to find change at a moment. Moments
then it
won't
would
show
equal
you
0
their
or
change.
something,
You have
wouldn't it?
to approach. Say again?
Then it would just equal 0 or something, wouldn't it? And that
It'd
would
be
be
0
correct.
over 0. Exactly right. So instead, let's try to massage this. Let's see if we can get an equation that will give us the same data. It will just not give us the same error. Okay. So what is one way that I can start to make this look different?
Well, we can convert 1 into a fraction and then add it to b over b minus 2.
Good. So what is the strategy you're employing there?
All right. The strategy I'm employing is that what I want to do is that I want to simplify the numerator, so that way later we can apply the rule that happens whenever a fraction is divided by a number, so a fraction above a fraction. But
I
we
like
can't
it.
do
So
that
what
unless
fraction should we make this into?
Hmm?
What fraction should we make this 1 into?
1 over 1.
If we did that, that would be good, but I still wouldn't be able to perform the addition.
Why is that?
Well, how would you?
Oh shoot, because of the denominators. Crap. All right, so after that, then we just got to multiply 1 by b minus 2 and multiply b minus 2 by 1.
That I like
in the
very much. Good.
denominators.
Exactly right. So let's make common denominators. That's the strategy I was looking for. So I'm glad you recognize that. So now I've got common denominators. In fact, if you want, we could even just simplify within this line. I don't think that's too much to ask. We'll just get rid of the 1 times, and we've got b minus 2 over b minus 2. This is fine. And now we can start to simplify that. Walk me through that simplification.
All right, so because both of the denominators are the same and they don't change via addition, they're just going to stay the same. What does change is the numerator, which now becomes b plus b minus 2, which is just 2b minus 2.
Good. I'm going to start to make that all nice and explicit. So we've got b plus b minus 2 over b minus 2 all in the numerator. On the denominator, we have b minus 1. This part here is the one that's the most difficult, I think, visually, but it makes sense if we look at it through the story. We've got b plus b, we've got a fraction, and then I'm trying to divide that fraction. I like to make that explicit sometimes and ask, is it okay that we write this as we've got our 2b minus 2 over b minus 2. That looks great. But instead of saying divide by b minus 1, is it okay if I say multiply by 1 over b minus 1?
Wouldn't it be the reciprocal?
Ah, good question. Good. So let's go ahead. Before we jump into this line then, let's write it even more explicitly. Let's write it like this. Are we good with that being the exact same story, different appearance?
Yes.
Good. So now if I want to say I want to divide by something like divide by 2, it's the same as multiplying by what?
It'd be the same as multiplying by the reciprocal.
Very good. So that's where in my work I was saying we could make this the limit as b approaches 1, and we'll have 2b minus 2 over b minus 2 times the reciprocal, 1 over b minus 1. Tell me if that looks good.
That looks good.
Good.
And
So now we
because
can
it's
go ahead and
multiplication, you don't need to worry about changing denominators and stuff. So at that point, you can just multiply everything over, and then we
good.
get
Love that. So let me catch up. So we got limit as b approaches 1 of, and now I've got 2b minus 2 on the numerator. On the denominator, I have b minus 2 and a b minus 1. Normally now is when the muscle memory starts to kick in and people start to see parentheses and say, like, let's distribute. But the whole purpose is I'm trying to cancel things away, and it's easier to cancel it away if I leave it as multiplication. So let's not make it addition on the denominator. Let's just leave it as this multiplication. And in fact, let's make more multiplication on the numerator. Let's make it 2 times b minus 1 on the numerator. And then on the denominator, I've got b minus 2 and my b minus 1. So we're making as much multiplication so I have as much opportunity to cancel across that division bar. What do you see?
Well, now we can cross out b minus 1 on the top and bottom, which just leaves 2 over b minus 2.
Very nice. So I've got 2 over b minus 2, which actually, as in this line, we are canceling away our divide by 0 error. Do you see that?
Yep.
So in that way, we now have a structure that's going to give us the exact same data. It's just not going to have that barrier at the end. So for our very last line of work, since I'm running out of some space here, our last line of work, we can just plug in 1 for
Oh,
b.
that's why it's -2.
There it is. So our very last line of work is we're going to plug in 1 for b, because now we've got something that's going to give us the data at 1 without the barrier at 1. So we'll do 2 over 1 minus 2, and that will be -2.
Ah. Man, if I had known that I could plug in if I could plug in 1 for b, then that would make this a lot easier. What I ended up doing was actually that I didn't plug in anything. I ended up simplifying everything down without plugging in any of the variables, and I ended up with a whole load of this.
Yeah, I
And yeah, it
mean,
just
this
got
one is
complicated.
definitely a lot of algebra. Now, one thing that I will give you as another takeaway that is insightful is you can actually graph these, and we'll practice more throughout the class how to graph these, but you can graph these quite easily if you know what details to look for. This right here is an equation where I've got, it looks like some kind of, like I've got a horizontal asymptote at 1, which we know because if I ran this limit towards infinity, that this would balance out with the same amount of growth on the numerator as on the denominator. So I've got some kind of like, I'm gonna get towards 1 as a height the further I go to the right. I'm gonna get 1 as a height the further I go to the left. And I also have a vertical asymptote at 2, because I would have a divide by 0 error at 2. So I could sketch in an asymptote at 2.
Where exactly did the horizontal asymptote at 1 come in?
Because if you did the limit as x approaches infinity of this, wouldn't that be 1?
Oh, good point. Good point.
And if you did it for negative infinity, it'd also be 1. So you got this idea of trending towards 1 as it runs off to the right, trending towards 1 as it runs off to the left. So we start to get this picture in our mind. And then it's a matter of, okay, how do these arrows connect? This one here becomes a little bit difficult. I like to just plug in a number. Like we could plug in a number like 1/2, right? This is at 2. So we could plug in a number like, let's plug in 1. Let's plug in 1. If we plug in 1, I get 1 divided by -1. That's a negative answer. So that must mean I get something that's like negative-ish down here. So there's my behavior. I've already got a pretty decent sketch of the graph. The graph is going to have asymptotic behavior, and it's going to run off like this. So this also lends a little bit of credence to why is the slope, why is the derivative negative? Well, because if I look at the tangent line right here, it is going to be sloping down.
Oh, okay. So it all
So
just kind of
there's
depends
multiple
on
ways to
where
like,
the vertical asymptote is on the graph and where you're going to be plugging in the number.
yeah, so there's many ways to approach this problem solving. Obviously, this method of sketching would not get us the -2, like that would not pop out of the sketch, and I wouldn't want to trust my artistic skills. But it's a nice way of just kind of double checking. So what I always like to do when I was working through tests is I would always just like do the problems, and then I would either go back through the problems I was unsure of, and I would solve them with different equations that I knew were just as true, or I would resolve them with the same equation, but I would not look at my answer, so that I just would double check my work, or I would try to sketch something and just make sure that the answer looked generally consistent. So how do you
Okay,
feel on
yeah.
that? Good approach?
Yep. I think
Excellent.
I'll plug it in from now on because I just feel like that's a lot more intuitive.
So yeah, but remember, plugging in the 1 in this structure would not have worked, because this right here just says, where am I? It doesn't say, how am I changing? So we've got to go through the derivative.
Yeah. I mean
Cool.
that's what I meant, so.
Good. Okay. Excellent. Yep. Plug it in after we do the derivative. Big fan.
but find it using the limit definition model. First off, are you going to specify, are you going to ask us for a derivative, and are you going to ask us to, um, use the limit definition, or is that a possibility?
Yeah. So if a question appears on the test asking about derivatives, if it just says find a derivative, again,
Mhm.
that means do whatever you want, right? Creative approach. You can use any of the tools we've talked about. You can, so long as they are exact, right? If someone's like, oh, I remember it means tangent line, so I drew a sketch and guessed, like I can credit that a little bit because you have some understanding, but that's not exact. We need one of the methods that gives us an exact answer. But power pattern for
Yeah.
derivatives is a technique, right? Using like the logic of the fundamental theorem of calculus, that's a technique. The limit definition is the literal definition, so of course that's a great technique. But which of those you use, whatever you want, unless I ask you like this one, use the limit definition. Then
Yeah.
I am looking for, can you actually use its meaning and show me that you understand how that meaning plays out?
Sure.
So if I specify, I want to see how I specify. If I don't specify, whatever you want.
Yep.
So on this one here, tell me what you're thinking about the limit definition of the derivative. Like what is that?
I'm totally at a loss as far as the limit definition.
Totally fine.
I've
So why don't we instead start from, tell me something about derivatives that you know to be true and makes sense to you.
Okay. I know that the derivative is the speed. It is the position, or the change in position over a certain distance and time.
I love that. Now we're going to start from that because that is literally all you need. Okay.
Yeah.
It's just that here, the change in position, I've got a delta x here when really the x, like we gotta concise the notation. Let's make this change in position. Maybe I'll make this change in maybe p for position. That would be fine. We'll make this change in position p. Okay. So that means change in position. Okay. Talk to me about how we find changes in position.
Changes in position is going to be, you're going to start at, you're going to take your ending point on, however you're graphing and modeling it, taking your ending point and subtracting your starting point from it.
Okay. So in this context, how would I find that?
So I think that, and let me just,
g prime of x, that was the derivative, right?
yeah.
Okay.
Let me see it's asking for you to find the derivative of 1 if g of x is x over x minus 2.
So how
So
does
the
g of x play
derivative,
into this?
beg pardon?
How does g of x play into this?
G of x is your, that is, I suppose it's both your starting point and your ending point.
So that's your position.
Yes. Yeah.
Okay. So now we can go with, instead of like delta p or whatever, delta time, like we can start to make this tie back into that's a good model, good logic. Now we tie it into the situation. So we're looking for where the g values change
Yep.
versus how the x values change, right?
Correct.
Okay. So
Okay,
that means if I
yeah.
want to figure out how they, go ahead.
Yeah, no, so that would be, the function there is your position.
Yes. Good.
Yeah.
Perfect.
So in order to find your, the difference in position, you would have to take one, whatever it is, one function and subtract it from another. So you
Good.
would,
One value of it and subtract it from the
yes.
other. So it's okay. So
Yeah.
we're looking at 2 different times.
Mhm.
Maybe we could write that like time 2 versus time 1.
Yeah.
And we're looking at what's my position at that time
Yep.
versus my position at the other time.
Yeah, correct.
Fantastic. Now this right here is just the slope. This is just the change. This is what we would call average speed because I've got a big chunk of time. How do I make that instantaneous?
Use your limits.
Limits
Yeah.
for what?
Limits from G or from X1 to X2.
Very good. I'm bringing those times close together. What you just did is you derived the limit definition. Like
Okay.
that's literally, you just made it. So let me show
Mhm.
you what it is according to the notes and let's tie the two dots together. So this is one way that it looks like limit as B goes to A of G of B minus G of A all over
Yeah.
B minus A.
Yep.
So what is the story here? It's literally, I'm looking at change in position versus change in time as I bring the two times closer and closer. Like you had that,
Yeah.
right? So sometimes I will use B's and A's just because the subscripts of 2's and 1's, they're a little dangerous with typos,
Yeah.
right? And this is a little simpler. There's another limit definition that is equally as valid, and that is the limit as h goes to 0 of g of x plus h minus g of x all over h. And what that's literally saying is that h is the time gap. H means the gap in time. So I'm making the gap between successive clicks go small, which means I'm looking at a moment h later versus some starting.
Yeah.
Now,
Okay.
either of those is fine to solve. Either one of those is fine to solve. Which one would you like to? Which equation?
Um, so I already started it on the first method, the top method, limit as B approaches A. Because I Googled the other one and it was just a bunch of letters
That's
to
fine.
me. Yeah.
Literally, both of them are fine. If you'd like, we can do them both. So let's run this one through. This one through. Again, we're just plugging in B into the function. So I have B over B minus 2
Yep.
minus A over A minus 2
Yep.
over B minus A. What am I
Yep.
missing?
The limit notation.
I have to have the limit. Otherwise, I'm not talking about derivatives anymore.
Yeah.
Now, at this point, do we have some more details like what time?
Yes. G of X is at 1. That's what
Oh,
it's-
okay. So we could
that's what
actually
it's
go all the way
saying.
back to here and say this is G prime of 1.
Yeah, G prime of 1. Yeah.
G prime of 1. So that means that my time I'm considering is as things get closer and closer to the moment of 1.
Yep.
So in the equations down here, where do I put that value of 1?
I put it in the A value.
It is the A. Yeah, exactly. Because that's what we're getting close to trying to examine more and more, right? So I can
Yep.
go through here. We can make this, I'll keep this as A in the beginning and show that we chose it to be 1 because 1 went along with our story. And we can also go through all of these other moments where I have an A
Mhm.
and I can replace those with 1s.
Yep.
And from here, we're just going to try to massage this equation so that we get another expression that gives us the same data, but does not encounter the same problem when I plug in 1 for B. All right, so we're going to try
Yeah.
to simplify this a little bit. First thing, let's leave that alone. Second equation or fraction goes down to,
It simplifies to a minus a negative 1.
good, good. So
So-
make that a plus 1.
Yeah, plus 1.
And then on the denominator, we have B minus 1.
Yeah.
What would we like to do from here?
Multiply. And this is where it it loses me because I'm thinking in terms of algebra. I'm not thinking in terms of calculus.
At this point, we've already set up the calculus, so I'm good if we just try to push it towards algebra. Like we have a very cohesive story, a very good
Uh-huh.
setup. Right now, we're in the act of just trying to simplify. Algebra can carry that without us having to exhaust too much brain power in what does everything mean, because there's equal signs between it all. It all means exactly the same thing as what we tried to make at the beginning. This is a derivative.
Yeah. But the problem I have, and maybe maybe the problem is that I'm skipping a step, is because, if we're, the limit is, 1 to 1. And, you plug in 1 for B, and you get a divide by 0 error. That's
Good. And
that's
that just
where,
means that we're not simplified enough yet to get an expression that allows us to collect the data. Like we
correct.
still need to simplify more.
Yeah. I'm at a loss as far as how to simplify this further.
Totally fine. So what I like to do whenever I'm like, if I was going to give you a commentary for my like thought process whenever I do algebra, I am
Okay.
honestly looking for just what is bothersome. And then I am thinking about things I can do to make it less bothersome. So what is the most annoying thing about this expression right now?
That we have a B in the denominator.
That we have a B in the denominator. Okay, good.
Yeah.
So we can go and say, is there any way to cancel that? No, because I can't like move
Well,
it very easily. If I divide the top and bottom by it, that's gonna like I'm gonna have to play with how that affects negative ones and positive. Like that's a little bit tough. So let's look for something else that's bothersome. What about the fact
okay.
that there's a fraction within fractions?
Okay.
Like I've
Well,
got
how
a whole
about,
top here that looks
how
somewhat
about
reasonable, but
multiplying by the reciprocal? Can't
I could do
you,
that.
yeah, divide the B minus 1, or multiply it by 1 over B minus 1, you would get, you would get a denominator of 1.
So you're saying
That
I
work
have
out?
the top, and instead of dividing by the denominator, I can multiply by 1 over b minus 1?
Yeah.
I love that. That's great.
Well, does it work algebraically?
But yeah, that's totally fine, right? Because
Okay.
the way that I would add some details in here is I would make it nice and explicit through the language. I'd say we had b over b minus 2 plus 1. And then instead of divided by b minus 1 written this way, I would write divided by b minus 1. The whole thing divided by b minus 1. And then this is just another way of writing divided by is multiplying by the reciprocal.
Yeah.
So that's totally fine. I'm good with that.
Okay.
What now?
Let me times B or X minus 1. You'd have to distribute that into because the denominator is going to end up being 1. B minus 1 over B minus 1 is 1.
Where do you see a b minus 1 on the top? I don't see a b minus 1 on the top anywhere.
I do not.
I like the idea of distributing.
Okay.
I'm going to propose, although we could make that happen, why don't we try to make this tidier?
Please.
So how could we add, like if I was just going to read this off as its general category, like this is just trying to add fractions, right?
Yeah.
How do we add fractions?
Cross multiply.
Yeah, that's a technique. Actually, I never do cross multiplying. I refuse to acknowledge that in any context in any of my math classes because it's one of the most
Okay.
errored techniques. But what if I just like made it simple fractions? Like how would I add those fractions?
Multiply the find a common denominator.
There it is, right?
Okay.
So let's do the common denominator up here. Right now, I don't have a denominator with my 1. I could make it a common denominator with my 1. So let's carry down what I haven't changed yet, b to 1. And then we have b over b minus 2. Haven't done anything with that yet. And then the common denominator would be what?
B minus 2.
So let's make this one a b minus 2. And the top becomes,
That would be a 2. Well, that doesn't necessarily work, does it?
let's try making it like this. Let's make it a 1 over 1 first.
B
And then
minus
if you
2.
want to make the denominator be a b minus 2, we're multiplying by b minus 2 on the denominator.
Yeah,
We'll also
It
do
would
that on
be-
the numerator to keep it balanced.
it would be b minus 2 over b minus 2.
There we go. Very nice.
Okay.
And again, like this is all being motivated by the fact that like I don't like remembering extraneous techniques. If I
Yeah.
already know a way to add fractions, then let's do that way of adding fractions, right?
Yeah.
So now that we have that, this says that I have b minus 2s, and I'm trying to add b minus 2 of the b minus, like what can we do here? Just what would we do with fractions?
Add the numerators.
Yeah, right. And it's the same idea as saying this is now 3/6 plus 2/6. So I'm just
Mhm.
following that parallel problem. So it's b plus b minus 2 over,
Okay.
Over
Over
what?
b minus 2.
Yeah, exactly right, right?
Now we get couldn't we, well, can we cancel out the b minus 2s?
If we don't know, then let's not worry about it yet. Because the only way we
Yeah.
can cancel it is if we're undoing something that makes sense undoing. Like we're undoing
Okay.
multiplication with division, undoing addition with subtraction.
Sure. Okay. You'd have to multiply the common or multiply the denominators, or you
We could do that,
find a
sure.
common denominator. In order to do that, you'd have to multiply b minus 2 by b minus 1. Is that
So be careful. If I did 1/2 times 1/3, do I need common denominator?
no?
So with this one here, we can also just multiply straight across.
Yeah, multiply the denominators. Okay. And yep.
Yep,
Okay.
so I've got b plus b. Can we make that 2b? Are we good with that?
Yeah.
2b minus 2, all times 1 is just leave it alone.
Yep.
On the denominator, we could write this where we multiply it through, do a bunch of distributing, do a bunch of factoring, but we have to remember that the main motivation we're trying to do here is we're trying to simplify. And the
Yeah.
way to simplify across a fraction is by making as much b multiplication as possible so that that division cancels it. So let's not like make it an addition problem on the bottom yet. Let's leave it as much multiplication as possible.
Yep. Okay, and then take the or factor the 2 out of the numerator. You
That
get
makes even
2.
more multiplication happen, which makes it even easier to find canceling.
Yeah. Yep. 2 b minus 1 over b minus 2 times b minus 1. Cancel out like terms.
Now, does it make sense why those would cancel?
Yeah, because 1 over anything over itself is 1.
Now, does it make sense from a not rule standpoint?
Well, yeah, if you're multiplying, you're just it's essentially cluttering up an equation by multiplying something that you could have in a simpler terms. Yeah, it's just clutter.
Yeah, it's the same thing as me saying I'm going to double your paycheck and then take half of it.
Yeah,
Like, what have I done? I've wasted your time. Like, I've
yeah,
done the change nothing for, so this is the same thing. I've multiplied and I will eventually divide by it. So yeah, we'll cancel those away. Notice that
mhm,
right there in this action, we have removed our divide by 0 error. Do you see it?
yes, because
Because
yeah,
had you plugged in for 1, that would have been a 0/0 error. Since we removed that first, and we were allowed to remove it because the limits weren't considering the at, we were considering the data on the way.
yeah,
Now I've got an expression that now I can use this for my data at the end,
yep. As B, approaches 1, eventually it's going to hit 1, so you plug in 1 for B, 2 over 1
which is why I
minus
stopped
2.
writing the limit notation, right? Once we
Yep,
considered its forever approach, I don't have to write it anymore.
yep, okay.
We'll
And
do
then that
-2.
gives us, yeah, 2 over -1 or -2. Okay,
So that one worked out very, but you see, like now, I think I've got another person who I worked with this problem through earlier. They did
mhm,
not do this first. They did the simplifying of the numerator with the common denominators approach
yeah,
first. But like, it doesn't matter because it's not about trying to do it one way. It's about trying to do it any way that is logical.
yeah, yep,
So to just kind of, so now that we have this, just because I think it's a fun comparison and it'll be good in the recording, let me go
sure,
ahead and take this now and shrink it down. And then I'm just going to smash through the math of this other equation so that you can see that this also would work. It's also a legitimate equation because, again, it's just a shift in our perspective. Instead of the first one, which says I'm going to bring 2 time intervals close together, this
yeah,
one says I'm going to consider as my gap in time decreases. It's like, oh yeah, that's the same story, just different equation. So let
yep,
me go ahead and put this one over here, and I'll make it a little smaller yet still. And let's take this away. Because I will say, when I was going through Calc 1, my teacher promoted the equation below the most, and I think that your book promotes that equation the most, and the YouTube videos all promote that equation the most. Why? I don't find it to be the most intuitive thing, which is why I don't teach it, but it does work because it's totally fair still. So we're plugging in x plus h into the equation. That gets me x plus h over x plus h minus 2. That's the later moment compared to the
yep,
earlier moment of x over x minus 2, all divided by h as I consider the limit for the time interval getting smaller.
yep,
So common denominator approach again would totally work here. That would be x plus h times x minus 2 on the top as well as on the bottom, x plus h minus 2 and then the x minus 2. So that's the common
mhm,
denominator for the first part, minus on the second one, I need to multiply by x and then x plus h minus 2 on both the top and
yeah,
bottom. Like it gets crazy, but thankfully we don't actually have to distribute any of it
uh-huh,
because we're trying to look for how it will cancel.
yeah,
So then on the next line, we say I have common denominators, so I can squish it all together. I've got x plus h times x minus 2, that's the first numerator, minus x times x plus h minus 2, that's the second numerator, divided by a common denominator of x plus h minus 2 times x minus 2. And then it's all being divided by h, so that's like having the h on the denominator as well, and we have this new limit.
mhm,
Now I do have a bunch of addition and subtraction, so I'm kind of forced to distribute it a little bit. I can do limit as h approaches 0. The first thing is going to get us x squared minus 2x. So I get x squared minus 2x plus xh minus 2h minus, on the next set of parentheses, x squared minus xh minus plus 2x all over h with all these things. And then I can simplify a bunch. This is an x squared minus x squared. This is a minus 2x with a plus 2x. This was a, I think we're just left with an xh minus h, minus 2h, excuse me, minus xh. So actually that goes away. We're left with minus 2h over h and x plus h minus 2x minus 2 limits.
Yeah.
And finally, the h's cancel away. I'm left with a minus 2 on the top. On the bottom, I've got an x plus h and a minus 2 and then an x minus 2. And then there's a limit. And then I can plug it all in. And then finally, I will get the exact same answer.
Yeah.
X minus 2 squared. And then we finally plug in 0 and we would get the exact same thing.
Yeah. Yeah.
Except somewhere here now I made a typo because I got exhausted. Anyways, it works. It's fine. I am now no longer a favorite of this formula. I like the other one because it's much more cohesive with the story.
If if you promise not to take it personally, I reached out to a family friend who was a Calc 1 teacher in Georgia on Sunday because I was beating my head against the table trying to do this.
Yeah.
And he gave me the second the second expression, or the second way of limit definition. And I was following along with your math in my work that I was doing here. And it's just it's both are kind of cluttered, and both are kind of noisy, and both are kind of algebra intensive. But I do agree that this, the first limit definition thing you got here is the lesser of two evils.
Yeah, they're both. I mean, yeah, they're both brutal.
Yeah.
So, which is
Okay.
why, like, we introduce it. It's like, hey, this came from slope. We understand why it took 1700 years for people to figure it out.
Yeah.
and then we move on. So yeah.
Okay. If you don't mind, just as far as find the finding the derivative of this equation at 1 using the power rule. That's just
This one won't allow the power rule.
okay. Yeah, because it's too small. Let's
Yeah.
say now I feel bad because I took up all of his time.
We've been bouncing around for hours, and I've still got 35 minutes of office hours. It's all trying to throw in as many people as we can.
Yeah.
Never enough time, and I don't have enough energy. I'm tired.
Yeah. So this wouldn't work using the power rule. Oh, that's probably why you gave us this question and specified that we use the limit definition model.
Yeah, so we will find, I mean, there's a shortcut for these problems. We will
Yeah.
explore that shortcut in unit 2.
Okay.
This one here is definitely this is the hardest problem of this category I would test you all on, because
Okay.
the algebra is it's intense.
Okay.
But it is within the realms of fair to ask. It's just it's just hard.
Yeah. Well, that makes sense.
So yeah, no, I have no problem if you reach out to the other calc teacher. Like I said, he's going off the book. I used to use the book. I had to make an active decision to choose to teach a lot of things differently, and I've got good reasoning for all of it. But yeah, sometimes, like, I am very different than the other teachers because I just can't seem to get students to memorize the other formula. It's after like years of trying, and then finally I was like, oh, it's because they don't understand it. Like, they have no idea what it is. So no wonder they can't memorize it. I'm literally asking them to memorize gibberish. So instead, I give them this, which they can all, like, y2 minus y1 over x, like, that's the slope equation. Limit attached to slope. Run it.
No.
At least this one, even if people mess up the algebra, if they write down that equation and it's correct to begin with, and they start it, like, if they get to here, if they get to that right there, I can give them a D, if not a C.
Yeah.
Right? Because That's at that point you would literally plug that into Wolfram Alpha, like the website, and the website would tell you the correct answer. Like I'm okay with that.
Yeah.
That's great for minimal understanding and credit in the course. That's excellent. You want to have an A and be able to tutor it, like you better be able to show them this. But like
Yeah.
at least this person knows what a derivative is and is no longer guessing.
Yeah. So just to kind of to wind back, get to the beginning here. The function there is the position. That is the precise point given the x input, the whatever, the function is, to show you where you're at. If you plug in, in this position, for like a speed equation, it would be your time. Okay. You give them a time, and you get that distance traveled. Okay. Then from there, the derivative would be the speed in that particular moment of time, right? The speed that is being traveled while the picture is being taken, right?
Mhm.
Okay.